All right. So today I'm going to present vector instructions using intrinsic functions. The other way to convey the same topic is to say single instruction, multiple data, or single instruction stream, multiple data streams. So we'll talk about SIMD. And this presentation is with respect to computer organization and design, and also computer architecture. So mostly I'll be talking about intrinsic functions that Intel supports. And we'll go to this website to see the list of intrinsic functions. So let me first talk about the context. So in computer architecture, we study about assembly instructions. So you may have studied ARM assembly instructions or x86 instruction set architecture, and there are many. So you basically write assembly instructions like move, add, and you use registers. Register 1, register 2, and then if your data is in registers, then you can do some computation like add on them. So this is what we study in standard computer architecture class. Now, what we want to do is build on top of this. So you can think of these instructions as scalar instructions, and we are going to delve into vector instructions. So we'll learn more about vectorization, how to use vector instructions, and our main goal here would be to learn about intrinsics. So intrinsics functions let us do vectorization, and let us use the SIMD concept, single instruction, multiple data. So what I'm going to basically cover in this lecture is basically extensions to x86 instruction architecture that supports using vectorization or using SIMD, right? So Intel Intrinsics are given here. So the introduction that I'm giving here will make it easy to navigate this page and make sense of what are the functions available there to do data movement and computations, and then how to use it, how to understand it, and how to use it in your own code. Now, what is the motivation for this lecture? The motivation is that learning about single instruction multiple data or vectorization will lead to writing code that has higher performance than what you get without using this feature. So using vectorization, generally our goal is to get a high performance code. So in compilers help us to translate high level code into assembly level code, and then further into machine level code, but the compiler translation is not optimal. So when we learn about intrinsic functions, we'll have more control on how to leverage this feature that is available in modern CPUs. Now, my lecture is motivated basically from reading computer organization and design book by David Patterson and Hennessy. And in one of the chapters, they mention this parallelism as subword parallelism. So what is parallelism? Basically, parallelism is basic idea where can do multiple instructions at a time in parallel to gain performance. And the book mentions this as subword parallelism. So what I've been mentioning as vectorization or SIMD, it's mentioned as subword parallelism. And the book contains some examples of matrix multiplication and how matrix multiplication code is accelerated using using intrinsics and by using SIMD instructions. So I'm basically building on that. The main motivation was that the book did not contain enough enough details on full program. So it has code excerpts, some code blocks, but it was not not enough to assign homework problems or to create lab assignments based on programming exercises, right? So this lecture will help you in doing that. So it builds on the available material. So I'll be providing code examples and some demonstration to make it concrete. So vector parallelism, we want to introduce vector parallelism. So if you use SIMD instructions, you vectorize your code, so you're getting parallelism by virtue of that. So you're using assembly instructions and hardware features to target data parallel execution. So data parallel applications are prime examples where you can use these concepts that I'm going to talk about to make your code run faster. All right. So my lecture is in two parts, part 1 and part 2. This recording is only about part 1. And there will be another recording for part 2. So in part 1, I'll talk about the conceptual ideas to get started, and the context is for computer organization and design class. So I'll talk about the basic ideas and then some functions. So these intrinsic functions are C functions, which you can make a call, use in your C programs or C++ programs. And these are a replacement of basic assembly level instructions. So the functions that I'm going to discuss will basically get translated into assembly instructions like load, store, and computation instructions like add, multiply, for example. And in part 2, I will show how to basically translate a loop, a C program loop, using intrinsics. And I'll demonstrate, that by using intrinsics, you get some performance gain. So your program gets speed up. I'll then also talk about aligned memory allocation. So memory alignment is important when we talk about efficiently implementing SIMD instructions. If the memory is not aligned, then either the code crashes or you get you don't get optimal speed up. So the implementation will not be very efficient. And I'll give the demonstration on Intel processors, but intrinsics should also work on AMD because they share x86 instruction set. And I'll talk about quiz, lab problems, and homework assignments that I have used. And I'll also provide solution to them. So part 1 continues. So the basic idea is that we know about standard assembly level instructions, and we want to now learn about parallel assembly level instructions. So can we exploit parallelism using assembly instructions? So that's the basic idea. So in computer architecture, this concept is a single instruction stream, multiple data streams. So there is a single instruction, but that instruction will work on multiple data, like array. So array has multiple items. So one instruction can process a small array. That's the basic idea. And our modern processors support extensions to the classical assembly instructions and the standard one. And these extensions are used, and there are many examples. So what I'm showing here are 3 examples. So SSE, streaming, SIMD extensions, SSE, then Intel Advanced Vector Extensions, so Intel AVX, and then AVX 512. And there are many more. And these are just 3 examples that are supported on Intel processors. And my examples would include AVX, because the book of the Patterson and Hennessy book also uses AVX. So I'll give my examples using AVX. So what would be an example to do SIMD where we can use SIMD? So one example would be you want to add multiple pairs of elements using one instruction. So let's say you have add instruction, and using that one single add instruction, you can add multiple pairs of elements, like 4 pairs or 8 pairs, so multiple pairs. It's because compilers support, compilers themselves will support, this conversion from, high-level code to code that uses SIMD, and that is called vectorization. Or there is another word, vector parallelism, which also means the same things. So in this lecture, we'll see some examples of parallel operations using instruction and registers, and I say wide registers here. So these are wider, means each register will be wide compared to the standard registers that we use when we do x86 or ARM assembly programming. So here is the example. So we have 2 arrays, A and B, and each array contains 4 elements. So A contains 1, 2, 3, 4. Array B contains 2, 1, 2, 0. So we could do addition of these 2 arrays, element-wise addition. So index 0 from A and B gets added, and index 1, and so on, right? So we can verify that the sum of these 2 arrays, element by element, is this. Now, the standard way to do this would be, you take add instruction, and there are 4 pairs of numbers that needs to be added. So there would be 4 add instructions that are invoked. Pound 1, pound 1, pound 2. These are just denoting that these are numbers, and these add instructions, you'll invoke add instructions and get the result in a register, right? So this is not the exact assembly instruction, but you can think of this as a pseudocode. So you invoke add instructions 4 times, and each add instruction will basically work on 2 elements and produce a sum. So this is a sequential way of doing, and we want to basically look at SIMD parallelism, right? So single instruction, multiple data. So the instruction that we'll use is add, and multiple data that we are going to use are these different elements. So now this example will show SIMD. So instead of doing add 4 times, in parallel, if you have to do the same thing, then there will be 3 steps. So let's say we have a new instruction called vector add or VAdd, and this is just an example. There is no instruction with the name VAdd. This is just to illustrate SIMD. So first you'll do a load operation. So the load operation will load 4 numbers into A, and then load B, which will load elements of B to the variable B, right? So each A and B now contains 4 elements each, and then the vector add instruction adds A and B to produce a result. So there are also 4 elements in the result, right? So this is an example of SIMD. So single instruction would be vector add, and multiple data are contained in A and B. So using one instruction, we are able to execute the summation of the 2 arrays, right? So depending on a implementation, vector implementation in CPU, we can potentially get faster, performance, better performance by using these vector instructions. And this is not intrinsic, so I'm going towards intrinsics. But this is, you can think of this as vector instructions. Now, what is important in my examples is to remember the width of the data types. So floating point, single precision floating point takes 32 bits. Double precision floating point numbers take 64 bits. Right, so this is just a recap. Now let's look at CPU registers, because we have to use registers to do any computation, and it's the same thing for scalar type or vector type. So we generally, depending on which assembly level language you have studied before, like ARM or any version of ARM, your register may have 32 bits or 64 bits. Right? So these are standard register size or width of the registers. The ones that we are going to use for Intel Intrinsics or SIMD or vector registers, they are wide registers, meaning if you compare them, 32 bits versus 128 bits or 256 bits. So there are different generations of registers and different generations of intrinsic functions, and the registers, they vary in the width, like how many bits can be stored in one register. So these are wide registers because you can see when you compare them, the number of bits that these special registers, SIMD registers or vector registers have is higher. So as an example, the one that we are using in this lecture, AVX instructions, so advanced vector extensions in the instruction set architecture x86, supports 256-bit registers, and there's a name given to that register, so YMM register. So you'll have register names like YMM0, that's the first one, YMM1, that's the second one, and so on, right? So there are multiple such registers. And each YMM register can store multiple data types. So floating point numbers takes 32 bits, and each YMM register can store many, like 8 or 16, depending on the exact generation of intrinsic. So wide registers containing more data types, many instances of data types. Now this example I've taken from Intel Vectorization Guide, which is available online, and they give an example of SSE, streaming extensions, SIMD extensions, and SSE2, which is the second version of SSE. So in the last slide I mentioned that the registers are wide. So in SSE, these registers, these vector registers, for example, can have 4 floating point numbers. And in SSE2, it basically shows that 128 bits can be used to pack different numbers of basic data types. So in 128 bits that is available in this cube, you can store 2 double precision floating point. If you just have to store bytes, then you can store 16 bytes. So that's what the 16 small cubes are showing. And if you multiply 16 times 8, you will get 128 bits. So 128 bits available in the register can be used to store, different data type like double or byte, short integers, 32-bit integers. So you can store 4 integers in 128 bits. That's what it is shown here. And for long integers, for 64-bit integers, you can store 2 of them, right? So this is how we are going to, populate the registers with numbers, and then we'll do operations on them. So you can think of the earlier example where we had an array, and the array could be, many elements of the array could be stored in one register. All right. This slide is also taken, this diagram is also taken from the same Intrinsics guide. And let's say you have a for loop, and the for loop runs many iterations, max number of iterations are there in the loop, and you basically do add operations between elements of A and elements of B, and the answer is stored in C. So this slide basically shows, without vectorization and with vectorization. So how does it look like? So if you don't use these SIMD registers, and that's called no vectorization, right? So vectorization is not invoked, is not leveraged. So these registers, these wide registers, do not get used efficiently. So only the first slot of the register is filled by the element of the array, and the rest of the slots, which could have potentially be, could have been used, is remained unused. So this is called, no vectorization of code that does not use vectorization. So we see that there is wastage of resource here. And if we use vectorization, if we use SIMD registers, vector registers, efficiently, then we are populating the registers with elements of the array, and then doing SIMD parallelism additions in parallel using the 2 registers, right? So this basically shows the high-level idea that you have to populate your registers with elements of the array A and B, and also C, and then you can do parallel add on these 2 arrays, right? So that's the basic idea. So you can think that you'll need 3 registers, 3 vector registers here for elements of A, for elements of B, and elements of C. And you have to reuse these registers depending on how much data you have. So it's a register, you can use it many times. Once you have done additions for for 4 elements and 4 elements, and you store that in memory, then the registers could be reutilized again, populated with the remaining elements of the array, so that you carry on the computations. All right. Now we'll see, how to translate scalar code to vector code. So scalar code means it does not use vectorization. How do we manually translate? So we'll look at that in more detail. So how to use these SIMD instructions, and we'll see some examples to do load, to do store, and to do add, multiply, and so on in C code using Intrinsics. And we'll use Intel Intrinsics functions. We'll not going to use assembly instructions. I'll show you that internally the intrinsic functions will invoke vector assembly instructions, but we want to use C functions to do that. Now, understanding how loop unrolling works will help us in translating the code. So we'll discuss loop unrolling. We'll see some examples. All right, so let's now talk about special assembly instructions. So you can use these special instructions, these intrinsics, or these vector instructions in processing images. So image processing, takes a lot of time. So if you can speed that up, then you get you get the benefit, right? You don't have to wait. So response time reduces. So I will talk about x86 extensions like AVX, but you have to understand that other assembly programming languages also support vector extensions. So in ARM, it's called Neon. All right, so let's look at the name of the registers. So in SSE2, the width of the register was 128 bits, and the name given to those to the registers were XMM0, XMM1. In AVX, the size, the width get doubled, so now each register is 256 bit wide, and the names are YMM0, YMM1, and so on. All right, so now let's look at some questions. In 128-bit SIMD register, how many integers and floating point numbers can be stored? So in this, you can think of float as single precision floating point number. Okay, so let's try to look at the answer for this problem. So the width of the register is 128-bit, and if we think of integer, an integer takes 4 bytes, and 4 bytes means 4 into 8, 32 bits, right? 32 bits. So how many integers can be stored in 128-bit registers? So you can just divide 128 by 32, and that will give you an answer. So the answer is 4. So you can have 4 integers and 4 floating point numbers in one SIMD register. So floating points, single precision, also take 32 bits. All right, now let's look at another problem, second problem. In 128-bit SIMD register, how many double precision numbers can be stored? So that would be 2, because our double precision numbers require 64 bits of storage. Okay, so 64 bits are required to represent one double precision number. So in 128, you can have 2 doubles. All right. And similarly, this could be your practice problem. So let's look at that. Currently, in 2021, the world's fastest supercomputer is Fugaku. It's in Japan, and it was made by a company called Fujitsu. And this supercomputer comprises of ARM processor, uses ARM instruction set architecture. Now, let's assume that this processor has many SIMD registers, and one of the SIMD registers is 2048 bits wide. Right, very wide register, 2048 bits. So how many double precision floating points can be stored in one SIMD register? That's the first question. So you can use the same idea as I provided earlier in the last slide to answer this question. How many characters can be stored in one SIMD register? So you can assume in C, a character is 1 byte. That means 8 bits. With that knowledge, you can see how many characters could be populated in one SIMD registers. The third question is how many pixels. So SIMD extensions are used in manipulating pixels in computer graphics and image processing. So there, 1 pixel is comprised of 3 bytes, 1 byte to represent red, and 1 byte for green, and 1 byte to represent blue. So 3 bytes. So how many pixels can be stored in one register? So these examples will basically, motivate you to think that a lot of parallelization is possible if we use wide registers. All right. So another question, another pop quiz. So assume a YMM register. This is the SIMD wide register with its 256 bits. So how many integers can fit in a YMM register? So we can solve that by dividing 256 bits by 32. And the second part is assume an array has 32 doubles. So this array has 32 doubles, double array 32. How many such registers, YMM register, can be utilized to process the array using SIMD? So how many registers can be utilized? So that's the second question. So let's think about this problem. All right, so here we have the answer for how many registers can be utilized to process the array that contains 32 doubles. So first we have to remember that double precision variable takes 64 bits of storage, and one YMM register is 256 bits wide. So one YMM register can hold 256 divided by 64, that is 4 doubles, double precision floating point variables. So 32 doubles in the array would require 8 YMM registers. Okay, so using arithmetic, you can find out that one YMM register can store 4 doubles, so you need 8 of them. So 8 times 4 is 32, so that verifies the answer. All right. So these questions should make SIMD registers more concrete. So now we'll be able to use them in doing computations. Okay. Now in intrinsic functions that I mentioned, and now let me show you the website that discusses the SIMD instructions, the Intel Intrinsics. So if you Google Intel Intrinsics, then you will get the Intel Intrinsics guide. So this guide talks about different generations of intrinsic functions. So since my lecture discusses AVX, so you can select AVX. So you'll see AVX functions, right? So if you open one such function, it provides you detail about that function. It also shows you that corresponding to this function, there is a vector instruction behind the scene. Like vadd_pd is for this function add_pd, and it also shows you the registers like YMM that I talked about. And in intrinsics, we don't use the register directly, but we use data types. So now I'll talk about the data types. Right. So we want to use data types instead of register. So let's try to compare them. So SIMD register YMM. One example is YMM0. In intrinsic functions, we'll use __M256D. D is for double precision. So here it is __. And then an example would be __M256D var. So now variable can be used like a wide register. So this variable can be initialized to store 4 numbers. For example, 0, 0, 0, 0. So this can store 4 because a double data type takes 64 bits and this has 256 bits. So you can store 4 double precision floating point numbers here. So the last slide only showed you double, but this slide shows you that if you include IMM intrin.h, then you can have, you can use these vector data types, intrinsic data types for integers, for floating point. This is single precision, and for double precision. So you can say int x or underscore underscore m256i and variable name. Now let me talk about loop unrolling, because once we understand loop unrolling, it is easier to convert a scalar code into vector code. So this is a popular compiler optimization. So let's see what this means. So this is a for loop that goes through different elements of an array and does add operation. So if max is divisible by 4, then we can translate or transform the code above with this one. So the loop changes. The increment part of the loop is I equals to I plus 4 instead of I plus plus. So here it increments by 1, here it increments by 4. And I chose 4 because in my examples, in AVX examples, if you are processing double precision floating point numbers, you could do 4 double precision floating point numbers. You can pack them in one SIMD register. So that's why I is equal to I plus 4. So it's because of my data type being double precision floating point number. And in the loop body, instead of having one operation, now I have 4 operations, right? Arithmetic operation, add, and add is happening on different elements. So you do 4 add on different pairs of elements from A and B, and then you increment by 4, and then do for I5, 6, 7, 8. So you do 4 things, 4 summations, and then keep on going. So if max is divisible by 4, then this will work. If max is not divisible by 4, then you have to do some post processing. All right, now if we want to compare this transformation with what it will look like in assembly level, then let's look at this, right? So the scalar code uses let's assume 32-bit registers here, R0, R1, R2. You could have 64-bit also, but in this example you have 32-bit registers. So you do a load operation for the first element of A, then load operation on second element for first element of B, and then you add them, and then you have to store them in C0, right? So this is how you write this one iteration of the loop this loop in assembly level, and you can think of this as a pseudo code. So it's not the standard assembly code, but you can think of the idea is highlighted here. And then this loop has to be it has to use some loop, right? So there would be a branch condition, and then there would be jump to basically implement loops. Now using unrolling, the way we have to think about it is that the unrolled, because we have unrolled this, now we can use vector operations. Like instead of scalar load, we can use vector load. So the load will now load 4 integers using one instruction. So if you provide an address of array A, that is the address of the first element of the array, then it will load 4 consecutive elements to register, or this wide register, SIMD register. You can do that for B, array B, and then do a vector add operations. So because our wide register contains 4 elements here, 4 elements here, so your answer will also be 4 elements, which is the summation, right? And then you store them in C. So this is showing you first iteration of, I mean, the loop body for when it goes inside for the first time, right? So if we unroll the loop, then we can see what is happening and can we do it in parallel or not. So it so happens that the different iterations of this loop are independent, so there is no dependency. So that's why we are able to easily unroll the loop here and then invoke vector operation. So if we write programs like this, even the compiler will have easier time translating or vectorizing the code. So this shows the picture from high level code to assembly level code, and how unrolling makes it easier to visualize using vectorization. Now this is an unroll practice, right? So once we have seen an example of unrolling, try practicing loop unrolling for this problem. So you have a array A, 12 elements are there. Then in those 12 iterations of the loop, you basically test if the number is divisible by 2, then print the number. So it prints the even numbers. So how to unroll the loop. All right, so hopefully you thought about this. You can even pause the video and then think about unrolling it. So similar to my example, you can have the 0th iteration, first iteration, second iteration, third iteration, and so on. You can unroll them and then jump by how many, the way you wrote the loop body. Right. So let's look at the one answer. So I've unrolled the loop body. So I plus 1, I plus 2, I plus 3, and everywhere we are doing modulo 2. So if modulo 2 is equal to 0, equal to 0, then you print the number and then you jump by 4. So here we jumped by 4, but we could have jumped by a higher number, and our loop body could have been even bigger, because now we're talking about integers. All right, but this is just an example of unrolling on a code that is different from the example that I showed you. All right, so once you have seen it, now once you have understood that, now what we want to do is given another code, how to use vectorization on it, or how to use intrinsics on this code. So that's what we want to cover next. So the data structure is same. You have A, B, C, 3 arrays. Each array has 256 elements. And now the loop has to do multiplication, pairwise multiplications. So you have array A, array B, array C. Now you're doing multiply. So 10 times 1 is 10, 11 times 2 is 22, and so on. So a bunch of elements. Think that this is 256 big. There are 256 elements here. So here you have to use a vector operation, vector instruction for multiply. Now, how many loop iterations do you need to use? So that depends on how wide the register is and what is the intrinsic function you are using, because you have SSE, SSE2, AVX. So depending on which one you are choosing, that will determine how many loop iterations you will use. So if you assume that you can, your register can do 4 operations at a time, then you basically divide 256 by 4. So that would give you the number of loop iterations that are required. So here the assumption is in the body of the loop, you're able to do 4 operations. And since there are 256 iterations here, so you divide 256 by 4. But if you are able to do, eight, you can do 8 multiplications. If you can do 8 multiplications at a time, then the number of loops that will be required is 256. 256, right? So it depends, right? Now in AVX, if you use 256 bits or to store integers, then how many integers can you store? So one integer takes 4 bytes. 4 bytes into 8 is 32. So one integer takes 32 bits. So 256 divided by 32 is 8. So you can actually populate 8 integers in one SIMD register, in one vector register. So your loop body can contain 8 integers. So 8 multiplications could be done by using one intrinsic function that does multiplication, right? So this is the back of the envelope calculation that you can do to effectively use intrinsic functions or use vector instructions. All right, now carrying forward, there are many ways to vectorize. The first one is to use directly assembly instruction. The second way is to use intrinsics, and intrinsics will get converted into vector instructions. And the third way is to use a compiler, and the compiler can also produce, can vectorize the code. We are focusing on intrinsics here. So let's look at some intrinsic functions. So underscore mm256 underscore add underscore pd with 2 arguments, x1 and x2 will do additions. So you can do additions on 2 input parameters. So x1 and x2 are the data types, and the data types are underscore underscore m256d and underscore underscore m256d. Right? So two parameters, and it will return you an answer. Similar to add, you have multiply, where you can do multiplication. So each of these intrinsics will use some assembly instruction like vadd_pd or vmul_pd. So v is for vector, and p is for packed, and d is for double. So you could call these functions, and these are SIMD because one instruction works on SIMD registers, but these SIMD registers are packed with multiple instances of basic data types. So that's where the parallelism is. And to look at the full details about multiplication function or add function, you should go to this website. All right, so here we are now looking at memory data movement intrinsic functions. So this is like load instruction, right? So in assembly we study about LDR, STRs to do load and store. In x86, the instructions are called vmove_apd, that is to store, and it uses registers. So the conventions are x86 conventions, right? This is the vector register with a percentage. So the intrinsic function that we'll use to do data movement from memory to registers is called load, right? mm256 underscore load pd, and we have to provide address. So this is the pointer to the memory. If it's a array, the first address of the first element you have to provide, and then whatever is in the memory will get loaded into this data type C0. Now, once you have done computation, you want to store the result in memory. So you have to provide the pointer or address, right? Address in the memory where you want to store C0. So C0 would be written to the address that you provide. Internally, both of load and store use the vector move instruction. So this is load, address is shown by R11 and data gets loaded into this register. And for the store, address is represented here, and then the data in the SIMD register gets written to the memory pointed to by R11. Right? So store YMM0 data into 4 C elements. All right. Now a practice problem for vector load. So let's discuss what is the answer for this problem. So we have an array, a double pointer ARR, and it contains these elements. So there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 elements here, and we call the load function and provide the address ARR. Name of the array is the address in C. It's a one-dimensional array. So what does C0 contain? So the options are 1 or 4 elements, consecutive elements, or C0 contains the address of ARR, or C0 variable now contains all of these. So what do you think? All right, so the answer for this problem will be the second one, and we'll discuss why it is the 4 elements. So we know that this variable contains 256 bits, and our double precision takes requires 64 bits. So 256 divided by 64 is 4. So this register can hold 4 doubles. So that's why the 4 consecutive doubles get stored in this variable C0. So the answer is 1, 2, 3, 4. That's the answer. All right, now let's look at the second pop quiz. So the same array. So we are doing load here, provide ARR, and then again we are doing a load operation and provide ARR4 as argument. So ARR4 is address of the 4th element, index 4, and the name of the array is basically address of the first element of the array. Then once we have loaded the elements from memory, then we are doing a add PD. So we're calling this intrinsic. So all of these are called intrinsic functions. So load PD, add PD, store PD, these are intrinsic functions defined in AVX. So what will be contained in sum, and the same sum we can store it in memory. So ARR4 is stored in memory. In the beginning, let's say it is all 0, 0. Then we are doing store. So whatever sum contains, we are storing that in ARR. So what will ARR contain? So what we are doing is overwriting this part. But first, let's discuss what sum contains. So A0 contains these 4. So that is A0. And then A4 contains these 4 elements because the starting address is 4, right? So 0, 1, 2, 3, 4. So that is what will be contained in A4. Now we are doing add, so element by element, the numbers will get added. So we have 1, 2, 3, 4, and then we have 5, 6, 7, 8. So this is A0, and this is A4, contents of these two SIMD data types, or the data types in the AVX intrinsic functions. So if we sum them, pairwise sum them, as we discussed in SIMD, 5 plus 1 is 6, 6 plus 2 is 8, 7 plus 3 is 10, 8 plus 4 is 12. So we get 6, 8, 10, and 12. Okay, so this will be our answer. B is our answer. Now we can think of, we looked at the data types supported by intrinsics, and we also looked at the name of the intrinsic functions like load, store, add. So now we are, getting ready to write our own custom code using intrinsic functions and intrinsic data types. So if you have, array A and B, and you have to store the sum in C, so there is a for loop missing here. So you can think that there is a for loop that goes through, all elements of A, B, C one by one and does this. Now how to, vectorize this using intrinsics, how to invoke the SIMD instructions, how to use vector parallelism for this code. So you can think of unrolling the loop, and these are doubles, so the loop body can contain 4 additions, and you can think of translating in that using that idea, this idea. So here I'm showing you more details. So our double has 8 bytes in bits, that is 64. So this is the loop using scalar C code, and this would be a vector code using intrinsics. So you use this, change the increment I++ to I+4 because you're doing 4 things. So you load 4 elements in A0, load 4 elements in B0, and then perform addition and store the result in memory C. So whatever the addition of the 2 subsets of A and B are stored in C, that is stored in memory. So you provide the address, right? So this is the basic idea on how you can use your Intel intrinsic functions in your C code. So code like this, will perform better, will run faster, because these are able to use SIMD instructions. Now there are a lot of functionality that these functions provide. So one was, load operation, which is vmove apd, as we saw. That's the vector instruction's name. We can also do add. That's what we saw in M256D add PD, and the corresponding vector instruction is vadd PD. P is for packed and D is for double. We can do parallel add, and it does 8 additions using 1 vector instruction. And we are basically interested to do that in intrinsic function, but intrinsic function invoke the vector instructions. That's why I'm showing you this. And it's also possible to use some masks. So for example, let's say you want to add some of the numbers, but not all of them. So you can also use those, you can do that. It's possible to do that. Like add should happen for some parts of the array, but not on other parts. So you can have some masks. You can have true Boolean array, true, false, and wherever it is false, there it is putting some other data values, but wherever it is true, it is doing add operation. A7 and B7 is added, A5 and B5 is added. So wherever it is true, it is doing the addition. Wherever it is false, it's not doing the addition, it is writing something else. It depends on how you use that vector instruction. You can also do permutation. So if this is your input array and you want to do some swaps, pairwise swaps, and write that into into output array, change the order. So you could do you have many vector instruction. One of them is vperm, ILPD, so the permutation, and you can tell the pattern by which the permutation should happen. So here 0x55 denotes this interchange or swap. So this example I took from High Performance Parallel Runtimes Design and Implementation book. So there are a lot of things that you can do. So moving data from memory to registers, doing some computation using masks, using permutation. So there's a lot of functionality available, and the Intel Intrinsics guide and the Intrinsics, if you do a Google search, you'll get the full list of all the instructions that Intrinsics support. All right. So now we have come to the last slide for part one, and we want to now do a recap. So we looked at our data types, underscore M256D for double. The motivation was that we want to use data types like in C instead of registers. And we looked at some intrinsic functions to do load, store, and add, and also multiply. We looked at loop unrolling for code transformation. So given a high-level C code, how to change the code so that it is easy to vectorize the code or use vector parallelism in the code. Right? So loop unrolling helped us to do that. All right. So in the next part, there will be some demonstration and some more intrinsic functions will be covered. All right, so we'll stop here. Thank you very much. Unshare.